So recall the last question, we're faced with the true and false question where f is R2 from R2 to R that is continuous in both variables separately. And we've shown that by a counterexample that this does not necessarily mean that f(xy) is a continuous function of two variables. But now what if we upgrade our condition from continuous in each separate variable to having the first partial derivative everywhere? So it means my del x of f and del y of f exists everywhere on R2. This is a much stronger condition, and if you recall from 2a or 2b, that if I have a function from R to R and that's differentiable, it must mean that the function is continuous. So this statement is definitely true for functions from R to R. But is it true for multivariable functions from R2 to R? Again, allow yourself to ponder upon this question, and if you think it's true, provide an explanation, and if you think it's false, provide a counterexample. So the answer to this question is actually false. So it means that our tried and true statement that differentiability implies continuity is false in two-dimensional cases. Whatever this sense of differentiability means. So let's see what a counterexample would be. So actually, the example from our previous problem, fxy equals xy over x squared plus y squared, or 0, depending on if x squared plus y squared is 0. This would also be a counterexample for this question. So let's just see, why does it have partial derivative everywhere? So now, by the previous problem we've done, I think it's clear that this function is discontinuous. This discontinuous at the point 0, 0. Right, this we showed with our last question. So what is del x of fxy if my x and y are non-zero? So it means if x, y not all 0, then this is just taking the x derivative, but fixing y as a constant. So this is ddx of f tilde of x, where f tilde of x is defined to be f of xy. And since this xy are not all 0, this is just xy over x squared plus y squared. And since x and y are not both 0, this is a perfectly good continuous differentiable rational function where the denominator never vanishes. So this is ddx of a rational function such that denominator is non-vanishing. So this always will exist. So this exists. We don't need to compute it explicitly. We just need to say that it exists for any xy that are not 0. So what if, and the same is true for del y, also exists. This is under the condition that x, y are not all 0. But if x equals y equals 0, what happens? Now, by definition, del x of f0, 0 is equal to the limit of h going to 0, 1 over h of fh0 minus f0, 0. But by definition, f0, 0 is 0. So this is the limit of fh0 over h. Since h is non-zero, we fall into this first clause here. So f of h0 is going to be h times 0 over something non-zero. So this is constantly 0. Same reasoning for del y of f0, 0. This is also 0. And so fx and fy exists for all xy in R2. And nonetheless, we know that fxy is discontinuous at 0.00.